Hi, everyone. Hi, welcome to the 2024 WMC Prizegiving. I'm going to call on Prof. Nandya Chetty, the Dean of Science, to get us started. Jenny?
Good evening, colleagues. I hope the audio is coming through. So it's really wonderful, a real pleasure for me to say a few words at the beginnings of this wonderful event, the awards function for the Wits Maths competition. So I want to recognize those very many colleagues, teachers and learners that are connecting up online from elsewhere in the country, but also from various destinations in Africa, and a very warm welcome to teachers and learners from many different schools in and around Gauteng, as I understand it. The Wits Maths competition was instituted in the year 2018, and I want to say, as Dean of Science of Wits University, this is really very close to my heart. I'm genuinely excited about its prospects for the future, and despite the COVID years, I think that we've really done magnificently from where we started only about 7 years ago. So there's been significant growth, and the impact has been quite marvelous. So I've got to start with a big thanks to Dr. Jonathan Curry. So Jonathan is principally involved in running the the Wits Maths competition, and he's been ably supported by Dr. Witwatersrand, who's done all of the IT support for the program. And of course, since we don't have a massive budget, it's been very difficult for us to fly students, teachers in from different parts of the country. And indeed, now it is an international competition involving many schools dotted around various African countries. The costs are considerable if we did try to get everybody together. But so the IT support, the interaction with our students, with our learners in this very broad spectrum of backgrounds is very important. So and I just want to recognize the support that's been given by Dr. Witwatersrand. So before I forget, I've got to recognize a few heads of school here. It's Professor Joe Moitseki, who's the head of the School of Computer Science and Applied Mathematics. So the Wits, even though it's the competition is associated with the entire university, it is really driven through the School of Computer Science and Applied Mathematics. So I just want to express my thanks to Professor Moitseki and his team for the support of this program over a number of years. And of course, we have Professor Simon Mukwembi, who is here. He's the head of the School of Mathematics. There's probably no place on earth where there's a separate School of Mathematics and School of Applied Mathematics at a major university. So just kind of gives you an indication of the importance that we hold for this discipline, which Professor Mukwembi always reminds me, mathematics as being the queen of disciplines. And I'm very fond of asking him, well, what then is the king of all disciplines? He hasn't been able to answer that question. I also want to recognize the Deputy Dean for in the Faculty of Science, Professor Willem Conradi. Thank you very much for being here, Willem. And Professor Willem Conradi himself is an accomplished mathematician. I myself am a theoretical physicist, so we are indeed in good company here. So I do want to congratulate all of the winners. This is, after all, is an awards function, so there are many different categories. We've now been able over the last couple of years to expand the competition to include learners from undergraduate, from primary school rather. So we start off from primary school, and we have age groups starting from primary school all the way through to various stages in high school, and it also includes the undergraduate students. So there are different categories here, and of course the teachers have been very instrumental in supporting the program, and of course ensuring that there's a good participation rate. The audio is not perfect here, isn't it? ensuring that that there's a good participation rate amongst learners from each of your schools. And I do want to thank our teachers greatly for this, because without your commitment and encouragement, we might not have the participation rate that we have enjoyed over recent times. And this program has grown considerably over recent times. I just want to point out that we've had 18,000, a record number of 18,000 participants in the first round. So we have, the initial round is located entirely within each of the schools, and that's a considerable number. And to manage all of that, Professor Ranchard, it's a huge effort. I want to thank you once again for coordinating all of that across many different schools, but also across many different languages. For the first time then, we've had exams in isiZulu, in Sesotho, in Afrikaans, and also in French. And I like the idea about incorporating French. We often forget about the Francophone parts of Africa, and I would suggest that a lot of the divisions within Africa and lack of cooperation, as I see it, has to do with linguistic barriers. So if we could make a bigger effort to work across the different language groups in the African context, it will surely bring us together. So I want to just make a few remarks about the importance of mathematics. Certainly as a physicist, I want to emphasize the importance of mathematics in critical, it is simply critical for scientific research and for basic development. It is indeed the language of science, and you could actually argue that science itself generated mathematics. It was not necessarily a one-way street. If you look at the work of Newton, and you will notice that he ran into difficulties trying to find a language, a quantitative language that would help him understand the motion of celestial bodies, and so he developed calculus. Was that not amazing that the science actually developed the mathematics rather than always thinking of it as a mathematics driving science? But mathematics is still very much an active field of research, and here at the School of Mathematics and the School of Applied Mathematics, we have active researchers that are publishing research in the highest international journals, attending international conferences, supervising students at the highest levels, at the levels of master's and PhD degrees. So mathematics as a research endeavor is still a very much an open field, and long may that continue. So mathematics is extremely important, not just in the field of mathematics and applied mathematics, but in the various different cognate disciplines. In physics, myself, in working in theoretical physics, have had to master all aspects of mathematics. And there's some beautiful aspects of mathematics that are applicable in physics. For example, complex variable theory. I've always marveled at the sheer beauty of the subject. Mathematics is used to model science, to test hypotheses, to analyze data in topics, in disciplines such as physics, chemistry, biology, environmental sciences, and so on. So it's important in advancing medicine. Climate science is an emerging area, and we need to understand and quantify changes to our environment. Just understanding what an average increase in temperature of 1.5 degrees Celsius since the industrial revolution, I guess, requires a lot of care. It's not a matter of just simply sticking a thermometer into the atmosphere and hoping to measure an average change in temperature of 1.5 degrees, but it is really a statistical argument, and you can measure temperature over a long period of time, and even though you have daily fluctuations around temperature, but on average you can, with very strong statistical arguments, conclude that there is indeed a measurable change in the average temperature around the world, and that of course has catastrophic implications for the ways in which we live our lives. So mathematics really underpins basic research, and that is unquestionable. But of course, mathematics is also very foundational for innovation. So here I now move into the engineering field, fields and look at ways in which engineering and innovation impacts on the ways in which we live. Computer science, data management, data science, various aspects of modern technology, cybersecurity, increasingly now artificial intelligence, machine learning, all of these having incredible impacts on telecommunications, digital media, all based on mathematical principles. So mathematics, at least in the realm of technological innovations, are critically important. Economic growth, mathematics impacts greatly on the economy, and it's quite noteworthy to recognize that a Nobel Prize is indeed awarded to the field of economics. And that is not just simply kind of sitting on a lounge chair and kind of pontificating and waving hands and making political statements, but it's based economics. The field of economics is based on quantitative understandings of different influences on the ways in which the various different economies develop. And so it's mathematics is at the very heart of that. It is a basis for us understanding finance, financial markets, and ultimately in the fields of actual science, it's so important for us to have robust ways in which we can manage our insurance systems, particularly healthcare systems in our country. So, and of course, mathematics being so critical to pretty much every scientific discipline and ways in which we live our lives, the skills that you develop by taking mathematics or by studying mathematics at various levels, I should state, from high school all the way through undergrad, postgraduate on to research, all of your endeavors in mathematics impart skills that are transferable to various other activities. It really enhances your employment opportunities. So I speak to all of this because we have real challenges in South African society, and teachers know this better than I do as Dean of Science, because I mostly sit in meetings and attend to financial matters in the faculty, and occasionally have to resolve issues within schools, within the faculty. But you are working with students that are often, or learners who are often struggling with mathematics. And it's a grave shame, I think, that many students, learners rather, are increasingly being encouraged to study mathematics literacy. There's no future for that at the university. In the Faculty of Science, if you have mathematical literacy, you have no chance of joining, of pursuing any studies in the Faculty of Science or the Faculty of Engineering, and certainly in the Faculty of Health Sciences. So please, I would really like to address that matter, because it really severely curtails the options of learners coming to university when they do not take the full mathematics. We have literally tens of thousands of applicants into the Faculty of Science, but we only take each year only a handful, just a little more than 1,000. So we do aim to take the very best of graduating high school students. And so the mathematics grades is really determines to the greatest extent whether we take students into the Faculty of Science, yet Wits or not. So given the challenges, the fact that we don't have a scientifically very literate society, and I think you'd agree with me on that, so we need to enhance and strengthen our mathematics education, and even if it's only at a popular level, even if it's only students that graduate with high school and go on to get a job, but there should be a genuine appreciation of the importance of mathematics. So I'd like to see us popularizing and getting much more of general society involved in understanding the importance of mathematics. And this is where the Wits maths competition comes into play, I think. That's why I support this and super excited about this, because it does precisely that. It gets young minds interested in the wonders of physics in a fun way. I've looked at some of the problems. Many of them are challenging, and I'm not so sure, Dr. Karu, that I'm going to be able to answer every single one of those problems. So I've left academia some time ago. But there's problems, many of the problems are genuinely interesting and really thought-provoking, and that's what we want. We want learners to be immersed in the world of mathematics and appreciate it for what it is. It is a beautiful subject. To watch the movie A Beautiful Mind, if you haven't, that's quite interesting as well, and tied in with mathematics, of course. So I would like to see us talk much more about mathematics around the dinner table amongst parents and learners, kind of understanding the importance of mathematics in ways in which it impacts on daily lives. There's an awful lot of mathematical puzzles and mathematical games and so on, which fascinated me when I was pretty young, already in primary school. And I'm hoping that those are the sorts of things that can be used to encourage young learners to get excited about the field of mathematics. So long may this competition continue. I'm really from the point of view of the Faculty of Science, and this is sponsored by the Faculty of Science, but also the Faculty of Engineering and the Faculty of Commerce, Law and Management Sciences. So the three faculties involved here. And I now just quickly want to recognize the sponsors. Jane Street Capital, based in the United States, is that correct? So out in New York, in Wall Street actually is connected with this program. How nice to see. And this company, Jane Street Capital, was also recently involved in sponsoring the Pan-African Mathematics Olympiad that Wits hosted just a couple months ago. The Wits Maths competition is also sponsored by Alan Gray, by Sharp, and of course by the three faculties within Wits University. Now, there are many regional coordinators that I want to recognize, not just within South Africa, but also from other neighboring African countries. I have the names of Aubrey Goagose from Namibia, Carla Hutting from Northwest Province, Godwin Olusegun from Nigeria, Ibrahim Simsek from Limpopo, Jessica Whitebreath from Rwanda, Joseph Domgo from Cameroon, Liam Baker from Western Cape, Linda Emery from the Eastern Cape, Lizanne Panamerba from Mpumalanga, Matthews Masola from Botswana, and Taryn Locke from KwaZulu-Natal. Also Teboho Kalili from Limpopo. Now, setting the exam questions can't be an easy thing. Each of these questions are reasonably unique. I would assume I've seen some of the exam papers posted on the website, but I'm assuming and hoping that each year we have a good number of new problems. So it does require a fair amount of thought. It's not easy. I know I've been through this, just setting an exam paper. It's not always straightforward if you want to set a fair exam paper. So it does require a fair amount of skill and attention to set a fair set of questions for the various different categories. So I want to recognize Bertin Zinho, Kalan O'Callaghan Kotson, Dylan Nelson, Evan Sneeman, Gabriel Diamond, Kalina Kramers, Graham Evans, Henry Gonin, Jacqueline Fenter, Jacques Duplessis, John Smith, Kathy Miller, Laura Gavin, Leonie Offmer, Leon Baker, and Phil Lobskachny for your contributions. That is extremely important for us to continue to maintain the high standards of the Wits Maths competition. So friends, teachers, learners, it leaves me then to wish you well for the remainder of this evening. Do enjoy your time here at Wits, and I hope to see many of you again next year this time. Thank you so much indeed.
Thank you, Prof. Chetty. So every year for the Wits competition, we have not one but two speakers. So we have two speakers for the Wits Maths competition every year, one local and one international. So I'm going to introduce our international speaker, who's Professor Valentin Gorenko, who's currently working at the University of Stockholm in Sweden. For those of you who've been involved in Olympiads for a while, if you know the yellow books, he wrote the first two of those on the pigeonhole principle. Blank on another one. I first met Prof. Gorenko. I was a grade 11 student, and I'd gotten dragged by my older sister to University Open Day. So being very much like the people in this room who are winning prizes, I decided that the natural thing to do was to go over to the math table and start asking them math questions. Fortunately for me, I actually got answers because Prof. Gorenko was sitting there. And yeah, welcome, Prof.
Do you want me to stand? Yes. Okay. Good evening. Can you hear me well? Good. Thank you. Well, it's a real pleasure and honor to have this opportunity to give this talk here. And I would like to first thank Jonathan for this very kind invitation. And as you heard from him many years ago, I'll not tell you how many, but many years ago, he was my student. And so he must have learned something good for me to invite me after so many years. We'll see. Well, besides this, I'm also quite excited to be here, and it's for several reasons. First one is that I now recall some 50 years ago when I was in your position and I was getting some awards from Maths Olympiads. So I really feel now 50 years younger, kind of. Oh, here is the second one. So as we people grow older, we start worrying about more and more things. Well, starting from how our individual life is going to end, and then after we are gone, whether the humanity will survive without us, and so on. And so one of my worries is actually this. I mean, with all the scientific and technological developments that we witness, I observe that the humanity has become lazier and lazier intellectually, and is willing to defer and leave in the hands of computers and intelligent agents more and more tasks and things to do, including mathematical tasks and problems to solve. And so that my worry is that one day maybe all of this will be left in the hands of computers and intelligent agents, and then what people will do is actually just only press some keys on the keyboard and then get the answers. And so that for me is really a frightening possibility. But that brings me to the title of my talk, whether this is possible at all. And so you are going to hear some answers. Now, let me tell you this. So shortly after I accepted the invitation, I actually realized how such a huge challenge this talk is going to be, because you are probably the most diverse audience that I've ever had in terms of your interest and your background in mathematics and all. And so I started panicking, and I thought, okay, what shall I tell all these people that would make sense to all of them and will hopefully be of some interest? So I said, well, maybe I can get some help from ChatGPT. And so I wrote some instructions. I said, well, write me 15-minute speech for, all these audience that makes sense and will be good. So after a long silence, ChatGPT said, sorry, I can't do that. I can't help you. So I was left on my own, and so this talk will be mine. Right. No, but I will really try my best. We'll see how that goes. But I will start with stuff that should make sense to every one of you, and then gradually, towards the end, I'll say maybe things that will be a bit more challenging. But I'll start with something very simple. So it's kind of a warm-up question. If I can get this going. No. Sorry. All right, good. So I'll say a few words as warm-up about why we actually like doing mathematics. But when I say we, I mean, let's say myself, but also the prize winners, not necessarily their parents, but let's say the majority of the people here. So the others just listen. So, we all ask this question ourselves from time to time. And so a typical motivation of a mathematician would be, because mathematics is interesting, or it's beautiful, or it's challenging, or it is abstract and detached from the reality, which can be messy and depressing sometimes, and so on. Well, but how about also being useful? And well, sure it is the most useful, and you heard that from the speech of the dean, and also you hear it from the next talk. But I will tell you something. So this is not really the typical motivation of a typical mathematician. Anyway, so eventually most mathematicians would agree that mathematics is a creative art, and this is, well, at least one of the main reasons why we like it. Now, so what do I mean by creativity? What is creative mathematics? What exactly is creative in mathematics? Is it to do numerical calculations, or geometric constructions, or solving equations, or differentiation and integration? Well, not really, because as you know, there are these very powerful packages now, like, well, Wolfram Alpha and others that can do all these tasks and much more, much faster and much better than most working mathematicians today, including your teachers and university professors. I mean, no, this is not a secret. Well, then what? Well, how about theorem proving using logical deduction, whatever that means? Not really, again, because there are already many automated or semi-automated interactive theorem provers that are implemented out there. So then, and besides that, yes, it's important that computation and deduction are actually the two sides of the same coin, but I will not have time to go into this. You are welcome to ask me questions after that, and I'll explain what I mean. So then what is left? Any suggestions from the audience? What else is it in mathematics? You should know this. How about problem solving? Okay, but then, well, so is it actually not true that every truth in mathematics can be computed or derived from a set of evident truths, as they call them, axioms, by applying formal logical reasoning, the kind of reasoning that you would see in mathematical books with proofs? And therefore, is it not then true that every mathematical problem can eventually be solved by a computer? What do you think? All right. So you're going to get some answers, and these answers would be answers from a logician. So I will actually tell you briefly and in very simple terms and with a lot of hand waving about some of the deepest and most fundamental results in mathematical logic from the 20th century. And so you will see at the end what the answers are. And I'll start with something very simple and very ancient. I'll start with the so-called liar's paradox, and probably most of you have seen it. You need to start with something that we all know. So consider this sentence: I'm lying now, meaning to say what I'm saying now is false. So is that true? Well, if it is true, then it's false by virtue of what it says. But if it's false, then it's true, because that's exactly what it says. So that's what's called a paradox. And this paradox was not discovered by me, sadly, but much earlier. It was discovered already, well, at least 4 centuries before Christ, and so it goes back to Eubulides, famous ancient Greek philosopher. And you will see shortly why I'm starting with the liar's paradox. It's not just to entertain you, but it will play a very important role in what will follow. So let me give you a more modern version of the liar's paradox, but it's still kind of non-mathematical one. It's called the barber's paradox. So the barber's paradox is about a village, a small village, which has only one barber, who is a man, and who is obliged by virtue. So his job description is to shave those, and only those men who do not shave themselves. All right. Is that clear? Well then, who shaves the barber? Well, he's a man. He needs to shave from time to time. Maybe you can say, all right, he never shaves, but he does. So who shaves? If he shaves himself, then he's actually violating his job description because he's not supposed to. But if he doesn't shave himself, then he must shave himself by virtue of his job description. And so you get the idea. There is again a paradoxical situation. Neither true, no, that is, there is no answer that is, well, let's say, consistent. Now, here is a more serious, much more serious version of the barber's paradox, known as Russell's paradox, and it refers to sets. So what are sets? I'm not going to define them, but think of them as any collection of things entities, and they are called their elements. So the elements, so a set consists of elements which are entities of any nature. And so some sets would contain themselves as their own elements, like, well, think of the set of all sets. So being a set, it must be an element of itself. Others not. Let's say the set of all people here is not a person itself. So then question is, well, here is a special set defined as follows. So it's a set R, which is defined to consist of those and only those objects, that is, those and only those sets that are not elements of themselves. But then the question is R an element of itself? Well, if it is, then by definition it is not, because it only contains those that are not elements of themselves. But if it isn't, then again, by this definition, it must be. So again, you see this same paradoxical situation where there is no answer which is really consistent with the story. If it is, then it is not, and if it's not, then it is. Okay, so this paradox was discovered actually just over a century ago by the famous mathematician, philosopher Bertrand Russell, and there is a dramatical story behind this, which I'll tell you very briefly. The story is related with this gentleman. This is the mathematician and philosopher, German mathematician and philosopher Gottlob Frege, who initiated a monumental effort to build the entire body of mathematics, derive the entire mathematical knowledge from purely logical principles. So what is logic, I'm not going to define here, but you all have some kind of intuitive idea. So this approach, by the way, is, well, let's say, one of the historically fundamental approaches in the philosophy of mathematics called logicism. So all mathematics is based on pure logic. That's the idea. And so he really wrote this fundamental book, in fact, 3 volumes, and the first one, called Foundations of Arithmetic, he developed and presented his ideas. And then the young Russell, then 20-something years old, read this book, and then he came up with this paradox. Essentially, he wrote a letter to Frege. Well, it's a wonderful book. There's just one tiny detail here that I'm not quite sure, so how about this? And so basically, Russell's paradox destroyed the mathematical foundation of what Frege was doing, and really dealt some unrecoverable blow to his work. So there was a drama behind this. But by the way, Russell himself essentially embraced Frege's logicistic ideas, and he subsequently wrote, together with Whitehead, a highly influential 3-volume book called Principia Mathematica, where he actually tried to realize Frege's ideas. Okay, so you will see shortly why I'm telling you all this. It's not just some important history. So next piece of background of what I'm going to say refers to the famous and probably world-leading mathematician at that time, David Hilbert, early 20th century, who embarked on this very ambitious program of building new foundations of mathematics, which will be free from paradoxes like Russell's paradox and others. And so Hilbert's idea, in a nutshell, was to develop the entire mathematics as a deductive system, a system of formal logical deduction, where all statements that you want to derive are formulated in a precise formal language, and the true ones can all be obtained starting with a few very intuitively very obvious claims called axioms by applying precisely stated rules of logical inference that derive new theorems, that is, new truths from already derived old ones. So the idea, Hilbert, was let's build a whole body of mathematics on very sound foundations as a kind of formal deductive system, which will derive those and only those mathematical statements which are true. That is, there are 2 main goals in Hilbert's program here. First is to develop what they call complete deductive system, which can derive all true statements about mathematics. And the second one is to actually show that this system is consistent, that is, it can never derive false statements, in particular, no contradictions. A contradiction, this is a statement and its negation. Or it cannot derive just, well, obviously false statements like 0 equals 1. So that was, in a nutshell, Hilbert's grand idea. And then, next, entered Gödel. At that time, young very young, in his late 20s, I think. Genius. He was indeed a genius, who proved in his doctoral dissertation, so that was actually his doctoral thesis, what is called a completeness theorem for the classical so-called first-order predicate logic, which probably most of you don't know what this is about. That is not important. Basically, this is a very universal and very expressive logical language where you can formalize all the mathematics that you guys know and almost all mathematics that is out there, so that it's sufficiently expressive language. And so what Gödel showed is that there is a deductive system. In fact, it was a version of axiomatic system that was already proposed by Russell and Whitehead's book, which is complete to derive all logical truths, not all mathematical, but all logical truths. That is, every logically valid formula that can be formalized in this language can be derived in that system. And so that was really very good news. That was a major step towards realizing Hilbert's problem. And then after Gödel did this, after he completed his dissertation, he was much more ambitious than this. So he really tried to show that not only pure logic, but also the entire, or at least let's start with arithmetic of natural numbers with addition multiplication. This is what you have studied from grade 1 and 2, can be completely axiomatized. That is, the system can be extended to derive all true statements about arithmetic of natural numbers with addition and multiplication. Sounds like an easy job, right? Okay. Well, instead, long story short, eventually he proved that this is impossible. And in the rest of my talk, I'll tell you, again, in simple terms, why actually this is impossible and what are the consequences from Gödel's discoveries. And so, well, Gödel's discoveries, they are summarized in two so-called incompleteness theorems, first and second Gödel's incompleteness theorem. I'll tell you in a nutshell, really on one page each, what they are about. So first, Gödel showed that in every sufficiently strong formal theory in the formal language of first-order logic that I mentioned about arithmetic, a typical example would be the so-called Peano arithmetic. So Peano arithmetic is a deductive system about what you can do with natural numbers with addition multiplication that essentially formalizes the rules how we add and multiply natural numbers, plus the principle of mathematical induction that most of you, the students here, know. So that's more or less what Peano arithmetic is. And so what Gödel showed is that if you have the system of Peano arithmetic plus possibly more, then you can actually effectively encode by means of natural numbers, like coding in let's say in cryptography, if you have heard, and so on. You can encode first all formulae in this language. Then you can encode the notion of a truth or derivation. And I'm not going in any details now, but ask me later if you want. And eventually you can encode the notion of a provable theorem, provable formula, or a theorem of your formal theory. Okay. And so now, here is the punchline. Then Gödel constructed this special formula, which I'll call GT. So it is given the theory T, he constructed this formula GT that essentially encodes the claim GT is not provable in T. That's the same formula GT. So essentially it says, I am not provable in the theory T. So it claims its own unprovability. Okay, what does that mean? We call Liar's paradox. There is a clear link here which I want you to think about and see where it comes. Now, notice, this is a statement. Well, this is the meaning, the intended meaning. This is what it says in terms of its, but it's a statement about natural numbers. So it's something like, well, I will not describe it because it is really technically involved, but it's a statement about natural numbers with addition multiplication. So eventually it ought to be true or false. Well, is it true or false? Well, the thing is this, if the theory T is consistent, that is, if one cannot prove false statements in this theory, then GT must be true. Because if it were false, then this would be provable in T by virtue of what it says being false, and this is provable in T, and so T can prove false things. So, assuming that this theory of arithmetic is consistent, that is, it cannot prove false things, then it must actually be true. And so there we have a true but unprovable statement. And so what Gödel showed is actually in every such a consistent, effectively axiomatized, whatever that means, and sufficiently strong, sufficiently expressive, and with sufficiently many important axioms and principles, arithmetical theory, every such a theory is incomplete. That is, one can come up with such a statement that is formalized in this theory, and it is not provable, because if it were provable, then this theory could prove false things, so it would be inconsistent. And so this is, in a nutshell, famous Gödel's first incompleteness theorem. And now, so notice, what that means is that, let alone the whole mathematics, even if you take arithmetic of natural numbers with addition and multiplication, you already cannot completely axiomatize it as a deductive system, let alone, again, the entire mathematics. So that sounds like a very heavy knockout blow on Hilbert's problem. And in fact, many believe that is the case. But there is more here. Maybe one can hope that one can at least prove the consistency of such sufficiently strong mathematical theories by means of formal deduction. So if we can't prove all the true statements there, then maybe we can at least prove that you can never derive false statements, you can never derive contradictions. So that would be something good. Well, so one can formalize this question in a, again, sufficiently strong arithmetical theory, whatever that means. One can define what one can call consistency predicate. So, okay, I will explain now what this means here. So inside you see this equation 0 equals 1, and most of us believe that this is false, right? 0 is not equal to 1. So this angle bracket here means that you take this statement and then you take the Gödel code. So it's a natural number which encodes this statement there. And then this THMT, this is, well, think of it as some formula that you feed a natural number. And if this natural number is a Gödel code of a theorem, that is something that you can derive from T, then this formula will be true or will return true, and otherwise it will return false. And lastly, well, this symbol here means a negation, so that the whole claim is that the statement here is equals 1 is not a theorem of the theory T. That is what is encoded in this statement. And so this is how we can formalize the claim that the theory is consistent. It cannot prove that 0 equals 1. Well, then the natural question is, but can this theory prove its own consistency? And as you might guess, in fact, Gödel showed that this is impossible either, unless the theory is already inconsistent. If it is inconsistent, then you can prove everything. That's how logic goes. So, if it is consistent, then it cannot prove its consistency. And this is Gödel's second incompleteness. Okay, so I hope I gave you some kind of fuzzy idea of these important things, and I hope that you got the message, and I will spell it out precisely, explicitly on my last slide, but let me first summarize. So, using some really deep ideas and techniques coming from mathematical logic, which is the area of my mathematical expertise, so I'm also running some kind of advertising speech here to attract young people to come and do mathematical logic. Gödel and other famous 20th century logicians have shown that the deductive method, the method of formal deduction in mathematics, has its unsurmountable limitations. And by the way, these are closely related to the limitations of the algorithmic method, of what you can do with computer programs with a computer for computing functions or for solving decision problems. In fact, in a sense, one can say that, again, these are kind of two sides of the same coin. I'm not going more details. But in particular, let me say this, that another famous logician, Alonzo Church, proved in 1936 that the question whether given formula in this classical first-order logic that I mentioned, whether this formula is logically valid, that is always true for logical reasons, or this question is algorithmically unsolvable, that is, it is not possible to come up with an algorithmic program, or program in a computer, that will always answer correctly this question. So, what is the conclusion from this? Well, put it in simple terms, the conclusion is that mathematics can never be completely formalized and can never be completely left to computers, it will always remain a creative area of applications of human mind. Or I'll put it in simple terms. Humans will never be able to eliminate the necessity of using their intelligence, no matter how hard and intelligent they try. And I want Thank you. And I want to use the opportunity to congratulate all the prize winners here and to wish you a very nice and enjoyable evening. If there are any questions, I'm prepared to answer, but I don't know whether there is time now, so maybe you can ask me later around here. So, John, you take over now. Shall I ask the questions now? Or? No.
Okay, so our next speaker is a professor at what is undoubtedly the best university in the world to be at. So I want you all to welcome Professor Ritesh Ajura from Wits.
Yeah, it's working fine. Thank you, everyone. My name is Professor Ritesh Ajura. I work at the School of Computer Science and Applied Mathematics, and my research interests are really in explainable AI, and I'll get to what that means in a few minutes. It basically centers around the idea that we should be able to explain the decisions that our AI makes so we can use them for problems where there are strong ethical considerations. I'm very mindful that the audience is quite inclusive. There are grade 4 learners with us, there are teachers with us, and there is also undergrad students. So what I wanted to do in my 20 minutes was to just introduce a simple concept in computer science, which is really what the success of machine learning, the heart of the success of machine learning really comes from. And this idea is to gain a likelihood estimate from some data. And I hope that everyone can understand this from the grade 4 learner right up till a university student. So there's hopefully something in here for everyone. So this concept is called maximum likelihood estimation, and some of you are familiar with it. But basically, it centers around the idea that you have some data and you'd like to learn something about your data. So the whole idea behind machine learning is really this. It's learning from data. If the machine learns from data, then it has some kind of representation, some way to perform inference, some way to learn the parameters included in the model, and some models can also make decisions. But all of these capabilities come from data. It always comes from data in machine learning. So so I am the director of the Wits Explainable AI Lab, and my students really work on representing really difficult problems where there are strong ethical considerations, like in medicine, like in education, in sociology, where we really need to know why the machine makes the decisions it does, the why, what really led to making that decision, what variables were involved, to what extent were the variables involved, what kind of methods, what kind of inference algorithms were used, and can we actually trace the input and output capabilities of these algorithms. So that's what my lab really focuses on. So it's modeling these problems, it's making decisions with these modeling techniques. And if we have interpretability, we have everything. We have causality. We can deduce causal relationships. We can deduce confounding factors, the variables that we can't always see. And we of course can run queries like what is this thing called interventions and what is it? Random control trials to deduce causal relationships. So that's really what I'm interested in. So does anybody know the capabilities of machine learning? Does everyone know what ChatGPT is? Everyone knows what ChatGPT is. Well, it turns out that machine learning is a lot more than just ChatGPT. There's a vast amount of capabilities. And what I tried to do on this slide is just to show you a few of the things that are happening in machine learning. So the last speaker was a pure mathematician, am I correct? Yeah, I'm a computer scientist. Not only, okay. But so I'm really interested in applications and using the capabilities of machines to help us solve problems that where there's a focus on the computational capabilities of the machine. So in machine learning, for example, we have a lot of interesting problems in drug discovery. where we want to be able to deduce how molecules actually behave under different environments. And if we can understand that, we can deduce what is the best effective treatment for this particular individual, whether it's for lung cancer, for any kind of cancer treatment. We really want to discover that. So this is called drug discovery, where we try to use the patient's individual attributes to be able to deduce what's the best drug that we can give this patient that will help them. Now, this is a very difficult problem. It's an extremely difficult problem, but it turns out that because of these, because of the virtue of the algorithms, the inference procedures, the way we represent problems in machine learning, it is possible to do this. Another interesting problem is in natural language processing, and this is where ChatGPT comes in. We're interested in sentiment analysis, where we want to deduce the sentiment, the emotion associated with a piece of text. There's machine translation, where we want to convert from one language to another. We all know Google has a website where you can just put in any phrase and get the translated phrase in any language. And there's a lot of things that go into that. There's the grammar, there's the sometimes symbolic differences in languages. So our machines have to be very intelligent to do that. Then there's computer vision, self-driving cars. In computer vision, we have object detection. If I have a particular object in front of the machine, can the machine deduce what is that object? Is it a glass? Is it a cow? Is it a student? Is it a table? Is it a desk? So the machine should be able to take in the pixel information as input and deduce what the object actually is. There's also face recognition. It's kind of the same concept, but with faces, with human faces. And image synthesis, which ChatGPT can do very well. You can ask ChatGPT to draw you different types of images. It's able to generate new images given some input data. In mathematics, there's also a lot of optimization algorithms, and I know that you probably know what that is already. But the kind of optimization algorithm that I just thought I'd mention is route planning. For example, if a particular individual wants to visit n number of sites, then what's the best way for him to do that in order to optimize efficient resource use? We have problems in climate change, and finally, algorithmic trading. Okay, so I just wanted to just give you a bit of a broader picture on what the capabilities of machine learning actually is, because a lot of people just look at ChatGPT and think that's all we can do. We can do a lot more than that. So this concept that I wanted to teach you, and like I said, this is for everyone. It's just a very simple concept in mathematics, in statistics. It's called maximum likelihood estimation. And what we want to do here is to be able to deduce, deduce a probability by optimizing that probability based on data. So in front of you, you have a small data set. And this data set is made up of, there's red symbols and blue symbols, there's triangles, circles, and squares. And so what we want to do here is be able to look at this data set and deduce the probability of certain things to happen. So there's a lot of notation there, so I'm going to explain all of it. But the first one, the P of R, is the probability of something red to occur. So who can tell me, how do you deduce the probability of a red object inside of this data set? There's a lot of smart students here. Yes? Sorry? For sure. Okay. So it's just a counting problem. We would just count the number of red objects and divide it by the total number of objects. And that's how we can calculate the prior probability. So we have the M of R, which is the number. So the M just means the number. This is the notation. We call it a sufficient statistic, but I don't want to get too technical. So this is the number of red items, 1, 2, 3, 4. That's where the 4 is. And then, it's shaking a lot here. And then the number of items M is the total number of items, which are 9 things. Okay, so if you just take that number, you have the probability of randomly selecting a red object in this data set. It's going to be 0.4, which is about 40%. You can do the same thing with blue objects, right? And so there's 5 blue objects altogether, divided by 9, which is the total number of objects, and you get 0.6, which is 60%. So the reason I'm showing you this is because most of the machine learning algorithms are based on this idea. Sure, there's more complex derivations like Bayesian estimation, which uses priors, and there's all of these more complicated things. But the heart of most of these algorithms is really basing the the likelihood of a prediction on that data to maximize that likelihood. So here you can also calculate what we call conditional probabilities. So what is the probability of a triangle given that it's red? In which case you count all of the triangles which are red, which there are 2, and divide it by the total number of red things, which there are 4. So can anyone tell me, how would I calculate the probability of a circle given that it's blue? All I would need to do, okay, I'll give you the answer because I want to move on to the next slide. So is to count all of the blue circles, 1, 2, 3, 4, okay, that'll be 4, divided by the number of blue items. So that's 1, 2, 3, 4, 5. Okay, and together we can deduce the following. This will be 0.8. On top here, I've shown you a little picture of a machine learning model called the Bayesian network. Now, I don't want to get too technical, but all of these parameters with some assumptions can fit very nicely into this network. And in this Bayesian network, it is interpretable. We can use it to actually explain the relationships between the variables which we see, in this case, the color of the object and the shape of the object, as well as we can impute these parameters in a very efficient way using these assumptions. So this is an example of a Bayesian network. And all of the applications, I'll show you 3 applications in the next 3 slides, are all the capabilities of this model to solve very important problems in our world. So let's look at the first problem. So the first problem, we're going to use this Bayesian network, which I showed you on the previous slide, to deduce learner attrition. So it turns out that deducing learner attrition is an extremely difficult problem. So what is attrition? It is when we look at a student's mark, or APS, the APS they got from high school, and we try to deduce whether the student will pass. It turns out that this is an extremely difficult problem, and mathematics can help us solve it. And why is this a difficult problem? So here we've got different risk profiles associated with different student outcomes. So you get no risk, which means that the student completes their degree in 3 years. They're a perfect student. They come in the system, after 3 years, they get the degree. Then you get low risk, is that the student completes their degree, but they take longer than 3 years. So maybe they take 5 years to finish their degree, but they do finish it. Okay, so it's a low risk. We have medium risk, and this is now where we have a big problem, because now we start wasting resources with a negative outcome. And medium risk is when a student, they take about 2 years, but then they actually fail out of the degree. Okay, so we lost some resources, the student lost 2 years of fees, and there was a negative outcome. And finally, we have high risk. The high risk students are the ones that take a really long time, 7 years, and still fail their degree. Okay, this is a big problem because now you have a lot more wasted resources than before. So the reason why I'm showing you this boxing whisker, this is called a boxing whisker chart. And the reason I'm showing you this is because this, on the y-axis here, this is what we use in South African universities to be able to admit students into different degrees. It's called the APS system. It turns out that the APS system is a really bad system to deduce learner attrition. Because this graph shows us that, this graph actually shows us that no matter, even if a student has my end is moving, I don't know why, but even if it has a 42%, I think this is not 42%, a 42 APS, there is no way for us to determine what would happen to that student. Everything is almost equally likely. So we need a more intelligible system that'll be able to deduce the output for us. And this is where we can use the model that I showed you on the previous slide, called a Bayesian network. Okay, this model over here. Okay, I don't know how much time I have, so I'll move a bit faster. Even if I have to skip the last slide, it's fine. So here we have this Bayesian network. If we apply it to a problem like this, we can actually deduce the probability of these different risk profiles given some information from the student, and we can do it really accurately. So this is a small app that I published with one of my students that is able to take in some characteristics of the student, individual characteristics, which is the choices the student makes, but most importantly, the grades the student gets in their grade 12 and deduces the risk profile. So I'm obviously not advocating for the use of this, but there is better ways of doing it. And the reason I'm not advocating for the use of this is because obviously there's different inequalities and different problems that we have to deal with. Okay, so now I want to move to the next slide, but how do I do that? Okay, is this, okay, so can I just press down? Okay, sorry about that. Okay, here's a bit of a slightly more difficult problem. So where are we going to use Bayesian networks from the first slide to solve an interesting problem in medicine. And the problem is that there's very little known about autism. So autistic individuals, their brains apparently are wired different from non-autistic individuals. They develop strength, they develop different connections in their brain, different types of connections in their brain compared to non-autistic individuals. And it's not understood why that their behavior differs significantly more from non-autistic individuals. So we can use Bayesian networks to help us solve this problem too, to at least be able to understand the different profile of brain activity so that we can help with early treatment and a whole lot of other things. So in this paper that was published at a very important conference in computer science called NeurIPS, Neural Information Processing Systems, this paper used a continuous version of the Bayesian network I showed you earlier. So in other words, continuous just means that instead of having this discrete types like R and B, we rather have a distribution over continuous values. So we would use this Gaussian graphical models to be able to deduce the different types of connections in the brain. So what you would do is you would take a bunch of individuals who are autistic and a bunch of individuals who are non-autistic, not autistic. You do a lot of MRI scans to collect data, and then train the Bayesian network to learn different connections in the brain. So it turns out that it's a very successful method to do it using maximum likelihood estimation to be able to discover the best model. And we are able to actually then determine what connections exist in autistic individuals compared to those who are non-autistic. Should I stop here for a question? Okay. So the final application I want to show you is basically plagiarism, a plagiarism problem that we have in school, at our university, not our university in particular, but most universities in South Africa. And this is where students use things like ChatGPT to be able to actually generate their code for them. Well, it turns out that your lecturer wasn't born yesterday. They can actually determine these things. And so here I am showing you an example of how maximum likelihood estimation, the stuff I spoke about a few in the second slide, can be used to discover knowledge, to discover the type of similarities between individual submissions so that we can actually find trails of similarities between students. So for example, this piece of code was passed around, went right around the class. And small incremental changes from individual to individual, but it can still be checked using this kind of technique. So that's all I wanted to show you. And what I really want to advocate here is the use for interpretable methods for machine learning. Thank you very much.
Awesome. Welcome, everybody. How exciting is this? So the Wits Maths competition started in 2018. So that makes this the 7th year that it's running, which is amazing. Thank you all for your support. I suppose if we tie in with one of the previous talks, if 7 is a complete number, then we are living in a 7th in a complete time. But I just want to describe a few of the considerations that we had when we came up with this competition. So one of the things we wanted to do is identify candidates who come from really disadvantaged backgrounds, because you can look disadvantaged, but if you go to a really top school, you're not really disadvantaged. You're not currently disadvantaged. So there's a well-known system in South Africa It's the quintile system. So how it works is quintile 1 is your least funded type of school. And quintile 5 would be your old Model C type school. So it's a government school, but it receives a lot more funding. And then technically quintile 6 would be your private school. So we give awards to people from the lower quintile schools, because those are schools where things are really disadvantaged, but those teachers are pulling their act together. They're making a big contribution to society, and we're very proud of them. Some of the other prizes that we've come up with is a Best Girls Prize. Obviously, in maths, you often don't have too many girls compared to guys, just the ratio is a little bit out. And so we just want to really honor those girls who are doing well, because it feeds into like the Pan-African Maths Olympiad team. And, there's great opportunity, and there's no reason why girls can't be just as good as guys writing maths. And then another thing that we have done is we decided we wanted to have some longer questions. So lots of the other questions that you'll see, the question papers from grade 4 onwards, will just be multiple choice. And, you get used to kind of guessing a little bit, and we wanted to have something that starts feeding into the idea of proper maths problem solving, which you see in the IMO and the PAMO, where you actually, it's not about how well you can guess, it's about being able to structure what you do. So we also give prizes to the best problem solving solution per one. So we're going to start with the middle primary teams competition. And the person who's going to be awarding that is Professor Simon McQuimby. So he's the head of school of the maths department at Wits. Thank you so much.
Okay. The winning school's middle primary is a Yelelo Primary School, notable quintile 3 school.
Is there anyone here from Intelelo?
Intelelo Primary School? Okay, we'll give them later. The second, Tamangane Primary School, notable quintile 3 school. Okay. King David Victory Park Primary School, 10th place, Gauteng. Lion School, Vida Park, 9th place, Gauteng.
Guys, please come up to receive your awards. Just anyone on the school.
No one from these schools? Okay. Woodlands International College, 8th place, Gauteng. Okay. Roydian School, 7th place, Gauteng. Yeshiva College Primary School, 6th place, Gauteng. Yeah, there is one coming there. Come get for the school. Thank you. Thank you, guys. This way, come this way. Yeah. Yeah. Okay. Lekang Primary School, 5th place, Gauteng, and Notable Quinta 3 School. Yeah, they are coming. Model Private School, 10th place overall. Anyone from Model Private School? Okay. Rarim Modern Learning Environment, 9th place overall. St. John's College Preparatory, 8th place overall, and 4th place Gauteng. There is someone coming. There is someone coming there. King David Linksfield Primary School, 7th place overall, and 3rd place Gauteng. Glenwood Preparatory School, 60th place overall. Anyone from Glenwood? Somerset House, 5th place overall. Trinity House Preparatory School, Rand Park Ridge, 4th place overall, 2nd place Gauteng. No? Yeah, the two, yeah. Yeah. Yes, come.
All right. It's later.
Okay, it's fine, they can come. Well done, guys. Bridge House School Preparatory, third place overall. Bridge House School, anyone? Okay. Sweet Valley, second place overall. Sweet Valley? Okay, okay. Thank you. Okay. Now, first place, Gauteng, first place overall, Red Hill School. Well done, guys.
To present the awards for the next category, the winning schools in the upper primary division, we've got Prof. Joel Moicheki, who is a very intelligent, good-looking, and wonderful person. I'm not saying that because he's my boss, I promise. Do you want to announce it? I think you can
Announce the schools.
Okay, so.
Which one? We can't see proper all day.
Okay, so should I read them?
Yes,
Okay.
that will do.
Okay, so Prof. Moicheki is going to present the prizes. The first prize that we're going to award goes to Ntwasa Shlobo Primary School, which is a notable quintile 2 school. Then we have a notable quintile 3 school in Chayalelo Primary School. A notable quintile 3 school, Lekang Primary School. Tenth place in Gauteng, Midland Primary School. Okay, is there anyone from Midland Primary School? We have 9th place in Gauteng, Rodin School. Eighth place in Gauteng, Jeppe High Preparatory. Seventh place in Gauteng, St. David's Marist Ilanda Preparatory. Sixth place in Gauteng, Hero Aurora. Fifth place in Gauteng, King David Linksfield Primary School. In 10th place overall, we have Selborne Primary. In 10th place overall and 4th place in Gauteng, we have King David Santon. In 9th place overall, we have Bridge House School Preparatory. In 8th place overall, the Ambassadors College, Ota. In 7th place overall and 3rd place in Gauteng, we have Laerskool Weerda Park. In 6th place overall, we have Edgemead Primary School. In 5th place overall, we have Red Hill. In 5th place overall as well, and 2nd place in Gauteng is King David Linksfield Primary School. In 4th place overall, we have Somerset House. In 3rd place overall, Sweet Valley Primary. In 2nd place overall, Glenwood Preparatory School. And in 1st place overall, in 1st place overall and 1st place in Gauteng, St. John's College Preparatory.
Yeah. So the junior secondary prize is the first class of named prizes, which is named after Paul Leridan, who wrote a lot of high school textbooks and put a lot into Wits education. And Prof. Konradi, could you present?
Okay. Thank you.
All right, notable quintile 1 schools, Mochwara Khole Intermediate School. And I just have to say, like, there are schools from far and wide. There's schools from Cape Town, schools from Rwanda, Nigeria, Liberia. So we fully understand when some schools were not able to be present for the prize giving. All right, notable Quintile 3 school. We've got Dendron Secondary School. All right. In 10th place in Gauteng, we've got Rodin School. 9th place in Gauteng, we've got Cornwall Hill College. In 8th place, Gauteng, we've got King David Linksfield High School. In 7th place, Gauteng, we've got Eduplex High School. In 6th place in Gauteng, we've got Woodhill College. In 5th place, Gauteng, we've got King David Victory Park High. In 4th place, Gauteng, we've got Midland Primary and High School. In 3rd place, Gauteng, we've got Saheti School. Polikala. In 10th place overall, we've got Graceland. Apologies, I work on a trading floor. We do things very quickly. All right, in 10th place overall, we've got Graceland International School, Port Harcourt. I think that's from Nigeria. In 8th place overall, we've got Adedokun International School. In 8th place overall, we've got we've got Fairmont High School. In 7th place overall, we've got the Ambassadors College, OTA. In 6th place overall, we've got Kearnsney College. In 5th place overall, we've got Petit Seminaire San Vincent Ndora. It sounds like a French school. Ever wonder? All right. In 4th place overall, we've got École des Sciences de. In 2nd place, Gauteng, and 3rd place overall, we've got Radio School. Then in second place overall, we've got Hope Haven Christian Secondary School. Then in first, and winning overall and Gauteng, we've got St. John's College.
Okay, we're now going to move on to the moment you guys have all been waiting for, not the individual awards, but the grade 10 to 12 team awards. And this one is another named one after Professor Peter Bridgeon, who was a professor in the stats department until he passed away in 2015. And yeah, I think let's, Goranko, can you present this?
Okay, so the next category is the winning schools in the senior secondary division. So first up, we have a notable quintile 2 school, which is Kweledi Secondary School. In 10th place in Gauteng, we have St. Stephen's Boys College. In 9th place in Gauteng, we have Seheti. In 8th place in Gauteng, and also a notable quintile 4 school, we have HL Setla Lentoa Secondary. In 7th place in Gauteng, St. David's Marist Inanda. In 6th place in Gauteng, Kensington Secondary. In 5th place in Gauteng, Eduplex High School. In fourth place in Gauteng, King David Linksfield High School. In third place in Gauteng, Sacred Heart College. In second place in Gauteng, Parktown High School for Girls. In 10th place overall, Rondebosch Boys High School. In 9th place overall, 4 Girls School. In 8th place overall, Welkin International School. In 7th place overall, Westerford High School. In 6th place overall, Petit Seminaire Saint Vincent Mindera. In 5th place overall, SA College High School. In 4th place overall and 1st place in Gauteng, St. John's College. In 3rd place overall, École des Sciences de Giseni. In 2nd place overall, Gracelands International School, Port Harcourt. In 3rd place, that seems like an error. That seems like an error. Okay, we'll have to figure that out. But for now, in 3rd place overall, Rondebosch Boys High School. There's still 2 more after this. We're good at math, not organization. In 1st place in Gauteng and 2nd place overall, St. John's College. No, something's horribly wrong here. Yeah, something's horribly wrong here. So, I can't tell you what's going on. We're gonna have to figure this out. Something's gone wrong. But first overall is the Ambassadors College OTA. Sorry about that. Technical difficulties. We're gonna blame technical difficulties.
Okay, so now we have sponsored talks. So we'll start with Andrew from Edinburgh.
Thank you very much, John. Good evening. Firstly, congratulations to all the students, and also congratulations to the WMC team for putting together a pretty incredible competition. This is a bit surreal for me because not too long ago, I was sitting in a very similar position to all of you, but now I'm on the other side of the stage, so to speak. Yeah, and as such, I am acutely aware of the fact that the last thing you guys want to hear is a long speech, so I will keep it brief. Yeah. By way of introduction, my name is Andrew McGregor, and I'm an investment analyst at Allen Gray. For those that do not know Allen Gray, we are an investment manager, which basically means that our clients give us their hard-earned brands, and they ask us to grow it. And in particular, we try to grow it better than the average investment manager, which it turns out is a very difficult thing to do. And as a result, we are always looking for exceptionally talented individuals, specifically ones with good critical thinking skills. And we believe that there is a very high correlation between critical thinking skills and strong performances in mathematics Olympiads, which is sort of what brings me here today. I would guess that actuaries, chartered accountants, and academia are sort of covers most of the career path that you guys are thinking about going into, and that very few of you would be thinking about going into career in investing. And I think this is because we market ourselves extremely badly. And so I'm here to change that. Or at least that's what I thought 8 years ago. Yeah. So I think when people think about careers in investing, images come to mind of Wolf of Wall Street and stock exchange floors and Bitcoin traders. But this is quite far from my day today. In fact, I spend most of my day just reading and learning. And that's one of the reasons why I fell in love with the job. And just to throw in the things there, the work-life balance is pretty good and compensation is quite competitive. So I would say that if you have a never-ending thirst for knowledge, you enjoy applying your mind on a daily basis, and you find yourself getting into debates just for fun, then I would strongly urge you to consider career in investing. I think most of you are quite far away from thinking about employment, but for those of you that have started to think about it, if you're interested, we do run a short internship at the beginning of the year, and if you want to get in touch, you can get in touch with me via LinkedIn, or you can contact John, he'll pass on our contact information. And for those of you that are not interested in looking for employment right now, I hope I've given you something to think about. Congratulations once again.
Thank you, Andrew. And now for a word from Sharp, who sponsored us as well, despite the fact that it's a contest which does not allow calculations during it.
Hello, everybody. I wrote notes, but they don't come in a pretty red book, unfortunately. All right. So, hello, maths nerds, and say that proudly, because it's awesome that you guys are the absolute cream of your crop. You are the top 200 out of 18,000 students. I did the math. It's 1.1111%. Okay. And so that's really incredible, and it's absolutely amazing. And so I'm going to give you a riddle to chew on while I talk to you, but still listen, please. Okay. So there's a story that goes that there was an emperor, and he had a problem to solve, and he asked the man, I'm trying to paraphrase this because I heard it a long time ago, but I want to get to the maths part of it. And so the payment was either to be paid in his body weight in gold, or to have a chessboard, and on the first day he would get 1 grain of rice, and on the second day he would get 2 grains of rice, and on the third day he would get 4 grains of rice, and so on and so forth, up to the 64th square. What would you choose? Okay, so think about that. And so I just want to say that I'm actually currently studying at Wits, which is really cool, and 2 of my professors are here, which is awesome. I'm doing a postgrad in data science this year, which has been mind-boggling and just incredibly exciting and just wow. Okay, and so I'm trying to balance 2 jobs, 2 kids, a husband who is my third kid, to be fair. And so I want to give you 12 things that I've learned over this last year, and hopefully maybe as you journey through school, because you are the top guys, you're going to need a little bit of a reality check. Okay, it's not just maths. Sorry. Yes, maths is wonderful and it's everywhere and it's very, very important. But there's balance as well. And so the first thing that I want to share with you is that you always make time for things that are important to you. So if maths is important to you, do it. Make time for it. If you like baking on the side, go for it. Enjoy it. Have fun with it. You know, not everything requires work. Okay. And then leading to that, sleep is good for you. Okay. You have some. Okay. Take a rest. Take your brain breaks. Go for a walk outside. Did you see this? It's beautiful. And so, yes, and I'm talking to myself here when I say take a brain break, because you do work hard and you do deserve to rest, and your brain needs that rest. And when you sleep, it does all of those funny, weird connection-y things, and it actually helps you with your learning. Okay, so don't stay up till midnight studying like me. Do it the right way and go to bed. Okay. The third point is it's okay to ask for help. And it's okay to say, I'm not managing all of this. Please just do one thing for me today. And leading on from that is find your team. So I have an absolutely incredible family that has really supported me through all of this, but I also have an amazing team at work. And so when I say, oh, they all go, it's okay, Tal, you can do this. You really have got this. And so find your team. Your team is here. You've got these incredible teachers with you. You've got friends who like maths. You've got your parents who are supporting you right now. That's amazing. And you are in the top 1% because you have that support. So rely on it. Use it. It's okay to say, oh, I'm stuck. Okay. Yes? Are you listening, or are you still thinking about the grain of rice? All right. Okay. The fifth thing is knowledge is powerful. And the way that you use that knowledge and knowing how to use that knowledge is powerful. And that's why I forgot my name. Sorry. The investment guru over here is reading and he's learning all the time, because as soon as you learn stuff and you know how to apply it, you're in that top 1%. Okay. It's okay not to be perfect. And failure helps us learn. And I will say this over and over again. When I wrote my matric, my June-July exams, I got 30% for maths. Okay, and at the end of the year, I got an A. Why? Because failure helps us learn. It motivates us. It teaches us new connections. Okay, and if you think about all of those great inventors, they all failed a bunch of times before they finally figured out how to do something. So it's okay to fail. Okay? Yes, Mom and Dad? Sorry. In saying that, find your passion. So I'm very lucky that I really love maths and stats and helping schools with maths and really encouraging maths community development. And I see so many teachers here that we work with all the time, and I always see their names. I'm like, I know that school, and they're just, what an amazing school to have teachers who are passionate about helping you achieve in maths. Okay. And then set your goals. Yes, I want to win the Maths Olympiad this year. That's my goal. Okay, I'll never win it. I'm not as smart. Okay, but I think having goals is an incredible thing. And then have fun doing it. It's okay to have fun, promise. Okay, so my other side job at S&D, I look after calculators, and then we've started a range of educational toys. And let me tell you, that is a fun job, because I get to take home all the toys and test them first before we even look at putting them on shelf. So have fun doing whatever you do. If you play cricket, or you play soccer, or you read a book and you enjoy it, that's great, that's awesome. You should really have fun while you do it. And then growing hurts, and that definitely links to failure, but failure helps us grow. So it's okay to be a little bit upset about stuff. But it's how you learn from that and how you grow from that that really sets you apart from everybody else. I'm nearly done. Number 11 is make semi-plans. And this is going to be my new favorite thing. I'm going to make semi-plans with you. And what that means is, yes, have a plan, have where you want to go, but remember to be flexible because not everything is going to pan out the way that you exactly anticipated. And you need to be prepared for that disappointment. When I started on my learning path a long time ago here at Wits, before they moved maths to this incredible place, I wanted to do educational psychology. And I absolutely failed at it. I didn't get in and I was devastated. And the reality is I'm not good at EQ at all. And I should never be a psychologist. But I discovered my passion for maths. And it set me on an incredible journey. And we've helped hundreds of thousands of kids with the worksheets and the YouTube videos that we do. And that, for me, has had a far greater impact than I would have ever had as an educational psychologist. So remember that what you think is a failure is not necessarily a failure. It's just to teach you to take it on. Okay. And then lastly, pay it forward. You have this incredible group of teachers who are helping you. You've got these amazing parents. You've got this great competition that you've done. How can you help those students who are struggling in maths? And we all know there's that one kid who doesn't get it, okay? So how can we help them learn? Kids learn better from other kids. So if you can help them, they'll learn far better from you because there's not so much pressure from the adults in the room who are watching you. Okay, so think about that. Use I wrote here, use your math superpower for good. So how do you use maths to make a difference in this world today? And we've spoken about the importance of maths, and I'm not going to go on about that, but it is. Maths is a superpower, and if you use it for good, we can change the entire world. Okay, so now that I have sufficiently motivated you, what would you choose? The body weight in gold or the grains of rice? Oh, you've heard this, haven't you? Oh. For those of you who haven't, I'm going to math it for you.
How about body weight in gold after eating it?
That's very smart. So for those of you who haven't heard the rhyme, but basically what happens is when you do this calculation, it's a beautiful exponential graph, and if you get to the point where the last grain of or last pile of rice is 2 to the power of 63, and I did this on the calculator, by the way, and that gives you 9.22 times 10 to the power of 18. Okay, so that's like billions and billions and billions of rice. So it would have completely, words have failed me now, I haven't had enough coffee. Thank you. Yeah, it destroyed the economy of this emperor who had come up with the solution. So just think about the power of maths and what you guys can do with that. Okay, awesome. Good luck and well done to the prize winners. You guys are amazing.
Okay, and now for the bit you've really all come for. Awards for fantastic service. Okay. Okay, so Manoy and Ruben, who I don't think either of them could make it tonight, but they've been just extremely helpful with the organizing of this competition, and I just wanted to acknowledge them for their service. We could not do this without them. Okay, and now we're actually are going to move on to the individual awards, which yes, I know some of you are interested in too. Do encourage you to use your math pass form. Okay, and Warren, can you present?
And could we just ask that the whole top 10 comes out and we'll take a photo all at once?
you give me all the difficult names to read now. Lupio Peko from Inchayamila Primary School. Notable quintile 3 learner. Onam Maksama, Ichiaelo Primary School, notable quintile 3 learner. Might be able to get this one right. Yamithle Bakanjani. I don't know if I get this one right. Zoe Annandale, Red Hill. 10th place Gauteng. Shang Meng, Red Hill, 10th place Gauteng. Kyron Thorilsley, Trinity House, 10th place Gauteng. Dylan McKay, St. John's College Prep, 9th place Gauteng. Labang Malepo, Trinity House, 8th place Gauteng. Teresa Smith, St. Teresa's School, 7th place, Gauteng. Oliver van Asweken, Laerskool, Garsfontein, 6th place, Gauteng. Evan Roos, Laerskool, Video de Park, 10th overall, 5th place, Gauteng. Daniel Malik, King David Linksfield Primary School, 9th overall, 4th Gauteng. Yaya Katrada, Glenwood Prep, 8th place overall. Cameron Evans, St. John's College Prep, 7th place overall, 3rd place in Gauteng. Miles Dixon, Red Hill, 6th place overall, 2nd place Gauteng. Again, okay. Logan George, Sweet Valley, 5th place overall. Mahira Sami Christella, Trust Mountain Academy, 4th place overall. I might need help with this one again. Ruta Bashiga Nezerwa, Trust Mountain Academy, 3rd place overall. Sam DeLonga, Sweet Valley, 2nd place overall. Li Fei Li, Red Hill, 1st place overall, 1st place Gauteng, best girl and best kid overall in Gauteng.
1 to upper primary, that's grade 6 and 7. Ronnie, can you?
Good evening, everyone. Mukona Nyase, Baila Primary, notable, Quinta 2. Morendeni, Kungo, Baila Primary, notable, Quinta 2. Pretty Rapunga, Baila Primary, notable, Quinta 2. Michael Grota, St. David's, Maris Inanda Preparatory, 10th place, Gauteng. Mikhail, I hope, Mikhail Tokan, St. John's, Gauteng, 9th place, Gauteng. Henel, Jivan, British International Preparatory School, 8th place, Gauteng. Urichen, Trinity, 7th place, Gauteng. Javulo, Utuli, Red Hill, 6th place, Gauteng. Eden Wright, College Preparatory, 10th place overall, 5th place, Gauteng. Okay. Joseph Moot, College Preparatory, 9th place overall, 4th place, Gauteng. Kobe Ochi, Pleroma International School, 8th place overall. Surich, it's Mutu, homeschool, 7th place overall. Ella Low, Glenwood Preparatory School, 6th place overall. Louis Bosman, Somerset, 5th place overall. Michael Tian, St. John's, 4th place overall, 3rd place, Gauteng. Yicheng Ning, Red Hill, 3rd place overall, 2nd place, Gauteng, best proofs, Gauteng, and overall. Celine, private homeschool, 2nd overall, 1st place, Gauteng, best proofs, Gauteng, and overall, best girl, Gauteng. Imra Adam, 1st place overall, best girl and best proofs overall, first perfect scorer.
Our next award is named after Professor John Kloffmacher, who, well, this is the grade 8 to 9 individual awards, named after Professor John Kloffmacher, who was a school in the maths department, and they'll be awarded by his son, Professor Arnold Kloffmacher, also in the maths department, but
Thank you. It's an honor to be presenting a prize named after my late father, who was a maths professor at Wits, working from the 1960s to the 1990s. In the late 1980s is when I joined the maths department as a staff member, and we overlapped for about a 10-year period, and during that time we actually worked together on research very successfully. But overall, I found that I had to keep on changing directions. One good thing about my father's speciality, it was number theory, and we heard the statement earlier that said that mathematics is the queen of science. Well, Carl Friedrich Gauss added to that, number theory is the queen of mathematics. Okay, I guess I'm ready now to. Shaku Todlo, Ranboteng High School, notable quintile 1 learner. Nicholas Schmidt, St. Stephen's Boys College, 10th place, Gauteng. Simon Grice Rand Park High School, 9th place, Gauteng. Chirag Naidu, St. John's College, 8th place, Gauteng. Sehuri Lai, St. John's College, 7th place, Gauteng. Richard Zhang, Saheti, 6th place, Gauteng. James Kerr, St. David's Marist, 5th place, Gauteng. Matthew Malak, St. David Linksfield, 4th place, Gauteng. Petras Bosman, Somerset House, 10th place overall. Zogsuan Liu, Red Hills, 9th place overall and 3rd place, Gauteng. Uemana Mugishi Anderson, Ecole de Science, 8th place overall. Ashar Johnson, Trinity House, 7th place overall and 2nd place, Gauteng. Joshua Scriber, Phil's Math Club, 6th place overall. Dayashimi Tasidi, Hope Haven Christian Secondary School, 5th place overall. Berwa Kasanyu Herv, Ecole de Science, Senior, 4th place overall. Ziax Yuan Lee, St. John's College, 3rd overall, 1st Gauteng, best group. Olivia Castledon, Somerset College, Hope, Hayes Christian School, first overall, best lady overall, best proofs overall.
And it's a tie.
And it's a tie. And here we have Puya Senge, Dennis Prince, Hope Have, Christian School, first overall, and also best proofs overall.
Okay, so the last two awards are also named awards. They're named after Peter Sonak, who's a Wits alum, who's been a professor at Princeton for the last 30-something years, and Professor James Ridley from Wits, who was his undergrad mentor. Usually when people find out I'm South African or mathematicians in other countries, they'll immediately ask if I know
teaching. The first is Amogelang Chingwaza, Witwatersrand Secondary School, notable quintile 2 learner. Next is Khonset Longwane, Witwatersrand Secondary School, notable quintile 2 learner. Lindo Gutle Sambo, Witwatersrand Secondary School, notable quintile 2 learner. Priyotsepile Lwate, HI Setlan Lentwa Secondary, notable quintile 4 learner. Kanokelo Makwe, Setla Lentwa Secondary, notable quintile 4 learner. Christian Pagenkopf, St. David's Maris, 10th place, Gauteng. Nicholas Christopher Delport, St. David's Maris, 10th place, Gauteng. Sky Smith, Taxian Oba, 9th place, Gauteng.
Harrison He, St. John's College, 8th place Gauteng. Armina Mayet, Parktown Girls, 7th place Gauteng. Laura Helling, Parktown Girls, 6th place Gauteng. Ava Fourie, Steyn City School, 5th place Gauteng. Neo Lissiliane Rodine, 4th place Gauteng, Best Lady and Best Proofs. Can I say I've had the privilege this year of being able to teach Neo, and it has been an honor. Rudolph van der Merwe, St. John's College, and 3rd place Gauteng. Noah Jacobson, St. John's College, 2nd place Gauteng. Sebastian Steer, Rondebosch Boys High, 10th place overall. Avaja Chidubim, the Ambassadors College, Ota, 9th place overall. Ellen Grant Smith, Westerford High School, 8th place overall. Eric Huang, Phil's Maths Club, 7th place overall. Ichagbe Jeremiah, the Ambassadors College, Ota, 6th place overall. James Prince, Sachs, 5th place overall. Gerard Dupree, Tuck Sianoba, 4th place overall, 1st place Gauteng, Best Proofs Gauteng. Jana Rousseau, Hoër School Jim Fouchier, 3rd place overall. Eli Williams, Westerford High School, 2nd place overall, Best Lady overall. Moyed Balek, Phil's Maths Club, 1st place overall, Best Proofs. These are the winners for the Peter Sarnak Prize. Wayne Hlungwai, Sifaku Makato, Health Sciences University, 10th place, Gauteng. Kate Edmonds, Wits, 9th place, Gauteng. Hamza Ahmad Karim, Wits, 8th place, Gauteng. Hayden Chong, Tux, 7th place, Gauteng. Fanelo Polite Baloy, Wits, 6th place, Gauteng. Maybe that's polite, actually. Mauda Wutuhu Huawe. Oh, that's Venda, I think. Wits, 5th place, Gauteng. Ting Lin, Tux, 4th place, Gauteng. Gerard Leroux, Tux, 3rd place, Gauteng. Corneille van Sale, Tux, 2nd place, Gauteng. Best proofs, Gauteng. Rachel or Rachael Side, Wits, 1st place, Gauteng. Best lady, Gauteng. Michael Louis Cronier, Stellenbosch, 10th place overall. Jordan Hugh, UCT, 9th place overall. Kerry Porrell, Stellenbosch, 8th place overall. Hayden Conradi, Stellenbosch, 7th place overall. Hugo Bruver, Stellenbosch, 6th place overall. Arabundade Precious Olamide, the Ambassadors College Ota, 5th place overall. Benjamin Klein, Stellenbosch, 4th place overall. Jason de Villiers, UCT, 3rd place overall, best proofs overall. Juliette Roux, Stellenbosch, 2nd place overall, best lady overall. Akinva Mofofokwa Excel, the Ambassadors College Ota, 1st place overall.
Hey everyone, so that concludes our award ceremony effectively. We will have eats outside. If people want to, talk to each other about mathematics, or I can't imagine talking about anything else, but if you want to talk about something else, you could. I don't see why, but you could. Yeah, so anyway, thank you everyone for coming. And once again, also there are pencils, rulers, and pens from Sharp. Thanks, Tom. So if people want to grab some, please do. And just another thank you to our sponsors, Jane Street, Alan Gray, and Sharp, and also to all the volunteers who helped set the paper and all the regional coordinators who
Maybe hospitals run.
And a big thanks to our organizer, John, who managed to pull it off. You see, there's an advantage when you have multiple choice. It's very quick to mark and you can get results around very fast. But when you have long proofs that are challenging, it's going to take longer. And this team is up to the task. So well done. If someone's lost the